schedule for this session, there were 3 speakers that now the second game. The first 2 talks were to be 30 minutes. Now the first talk is going to be an hour, and the second talk is not going to be at all. So let's make that change. So our first speaker this afternoon is Zemlyanova from Kansas State, and Anna's going to talk about contact problems at nanoscale.
Thank you very much, and thank you for coming to my talk after lunch. So today I will talk about some contact problems in linear elasticity, the difference between my problems and the classical problems, which you will see, is in boundary conditions. So I have unusual boundary conditions. And what those conditions do is they attempt to emulate problems at small scales. So in this particular case, at nanoscales. So when we talk about nanostructures, and there have been a lot of discussion about various nanoscience problems lately, there are 2 characteristic features which are essential for me and for this talk. First of all, characteristic length scale is typically anywhere between 1 to 1,000 nanometers, so hence nanostructures. And another characteristic feature is a high surface to volume ratio for nanostructures. So when we talk about nanostructures, surface area plays a prominent role. And here is a nice picture which I took from nature. So those are so-called nanoflowers which these people created. So now nanostructures play an important role in many areas, industrially important areas. They allow to make our devices smaller and correspondingly more comfortable, more convenient for applications in medicine and so on and so on. So there are lots of applications for this. In particular, there is a lot of industrial applications for nanocomposites. And one of the things which has been noticed for problems at nanoscale is that they are very much size dependent. So if your structure becomes smaller, so for instance, these cylinders, inclusions here become smaller, then the properties of the structures change depending on this size. So your composites may become stronger, may start exhibiting different properties, which is not explained, cannot be explained by many classical bulk theories. And one of the theories here is that surfaces are at least partially responsible for this change in properties with size. So if we talk about nanostructures, here is a picture, illustrative picture. If we look at the cube and we take 1 centimeter cube, then it's easy to compute surface area, 6 centimeters squared. Now, if we break this cube into 1,000 smaller cubes, but suddenly the same volume possesses a surface area of 60 centimeters squared. Now, if you keep breaking it up, the area becomes larger and larger. So nanostructures have high surface to volume ratio. And surfaces, to some degree, can be viewed as a defect in a material, as a special place in the material. So they have different coordination number. Atoms might have dangling bonds, since there are no neighbors on the other side. They rearrange. Atomistic structure itself rearranges. Moreover, surface, on macroscopic level, surface might be contaminated by inclusions and impurity. For instance, you might have oxidation on the surface. And on top of everything, you can also have coatings on the surface. You can have coated structures. So all these different surface properties can be, to some degree, modeled by those models which I'm going to talk about today. So what is the main idea here for modeling of these surfaces? So we have a solid object, omega, and for this solid object we assume standard linear elastic energy, W, so in a standard form, nothing special there. But then on top of everything we will also look at this component. So this is this component is U is responsible for the energy on the boundary. So we augment our model with a surface energy. Now, there are different ways to model with U. So the models I'm going to talk about are by no way unique or exhaustive. Again, it depends on what kind of properties you ascribe to your surface, what you did to your surface. So in this particular example, I will be talking about surface energies U, which are dependent on two things, on surface stress tensor and on surface curvature tensor. So you can think about this as your surface being resistant to stretching and being resistant to bending. So this is essentially membrane theory for the surface. Now, two big theories in this area. This particular area is, of course, celebrated Gurtin-Murdoch surface and elasticity model. So it has been proposed a while ago in 1975, and it has generated an enormous amount of research. So there are thousands and thousands of papers dedicated to Gurtin-Murdoch surface elasticity. And in particular, it has been successful because it showed good agreement between modeling of nanostructures and real life. So there are lots of papers dedicated to this theory. And you can think of Gurtin-Murdoch model as a thin layer attached to the surface. And this layer is a subject to pre-stress. So you can have pre-stress, and you can have resistance to stretching. It does not, Gurtin-Murdoch surface elasticity does not resist to bending. So, and there are many relevant, many works relevant to this in this area. Some of the most relevant and close, what I'm going to talk about, have been done by Schiavone-Roux and their team at University of Alberta, based mostly at University of Alberta. Sonia Mogilevskaya, who is another participant in this program, who is not here today, and her collaborators, correspondingly mainly based in University of Minneapolis, and there are some other related works in this area as well. Now, the model which I will describe today goes actually one step further compared to Gurtin-Murdoch model. So in 1997, 1999, Steigmann and Ogden wrote the two fundamental papers about enhancement of Gurtin-Murdoch theory. And what we noticed is that Gurtin-Murdoch theory cannot actually support compressive stress states. And that is supposedly the application which it was created for, to model these compressive stress states. And they suggested augmenting their theory by additional resistance to bending. So what it led to mathematically, it led to incorporation of curvature-dependence into your surface energy. Correspondingly, it made the model more complicated, high order, but it resolved this paradox of compressive stress states. And this theory is relatively new, and it's becoming more and more popular lately. So I see more and more papers showing up on this. And it really just, oops, sorry about that. And it was really just starting from 2016. So a paper in 2016, Yeremiev and Lebedev published their paper about Steigmann-Ogden surface energy. And what was interesting about that paper, one of the things which was interesting for me among all other things which were in that paper, is that they derived boundary conditions for Steigmann-Ogden surface elasticity in that paper. Before, Steigmann and Ogden published their paper only in terms of energy, so there were no boundary conditions. Correspondingly, there was little research generated, little solution for problems generated by this. But after this paper in 2016, there was kind of mini explosion, maybe, of works in this area. And in particular, what has been done so far is straight fracture, mode 1-2 straight fracture, plane fracture. There were solutions to plane contact problems, which I'm going to talk about today, to study of nano-inclusions, which is a very practical problem, so circular nano-inclusion and spherical nano-inclusion. And lately, there are also works on axisymmetrical patch load problems, which I also mentioned briefly. So there are lots of papers right now, and there are some advantages to this. So what this is, in the bigger picture, is an attempt to model essential atomistic interactions through continuum-based approach. And of course, if we use continuum-based approach, we are not stuck resolving any individual atomic interactions, because even nanostructures have a lot of atoms, individual atoms to resolve. So it's computationally easier in many ways, and it shows some promising results, maybe. So it's based on physically valid assumptions. It's governed by a relatively small number of parameters, unlike some other things. For instance, processing zones have a lot more parameters attached to them. So here there are typically just a few parameters which your surface energy depends on. And an interesting thing about this theory is introduction of surface energy actually introduces a length scale into your problems. So suddenly your problems with linear elasticity, which is scale independent, become actually size dependent. So that is an interesting result of this. Since its bulk theory is the same, linear elasticity, and standard techniques are somewhat valid for solving of these problems, and hence complex analysis. So one of the main tools of two-dimensional linear elasticity still works to some degree in this area, hence my talk. And it can be incorporated into finite element codes with some difficulties. There are some difficulties there, mostly because you have to have smoother, nicer elements near the boundary. So, and another unexpected result here, somewhat unexpected, is that introduction of surface energy actually results in smoother solutions. So for instance, for crack, classical singularities of order 1/2 might disappear. So might actually have bounded stress and strain fields if you introduce surface energy. So there are some interesting results out of this. So now let's talk about governing equations. So if we take that energy functional formulation and we apply divergence theorem, surface divergence theorem, then we get this classical bulk conditions. I assume that bulk force is 0, so no gravity, no nothing. And on the boundary, we obtain this condition. So if you look at this, this is just a surface traction, so normal times jump in your stress tensor for the surface. This is just exterior forces applied to a surface. So again, that is classical. And then you get this TS component. And TS component is exactly what comes from your additional surface energy. Now, what is this TS component? So for classical Gurtin-Murdoch model, this has been known for a while and has been used by many people before. This TS looks like surface divergence over surface stress, and surface stress is taken in this form. So sigma 0 here is a pre-stress, so your surface can be pre-stressed. Lambda 0 and mu 0 are essentially surface Lamé parameters here. So 3 constants total, and A is a projection tensor, epsilon s is a surface strain tensor, and this is the energy which is usually used for Gurtin-Murdoch model. If you look in the literature, you can see that there are some curtailed Gurtin-Murdoch models. So this is a full model, but sometimes you will see what problems where people drop this term or more rarely drop this term. So it's kind of modifications to model. There are again lots of papers dedicated to this particular type of surface traction TS. Now, Steigmann and Ogden model is an improvement in some ways on Gurtin-Murdoch model. So still have this Gurtin-Murdoch component over here. So everything which was on the previous slide goes here. And then you have these 2 additional components which are higher order components. So in Gurtin-Murdoch model, you typically have 2 derivatives of displacements. So your stress interactions on a boundary depend on 2 derivatives of displacements. In Gurtin-Murdoch model, you actually get 4th derivative of your displacement. So it's high order model because of that. And again here, so this is all the quantities, tensor quantities which go over here. And this is the surface energy. Again, it looks like Gurtin-Murdoch, except for here you have this curvature-dependent component. And zeta and eta are those parameters which regulate how resistant your surface to the bending. So again, my main tools in complex analysis. And in complex analysis, we are somewhat restricted to two-dimensional problems, right? So there are some favorite toy problems here which we can solve using this theory. And of course, the simplest one probably, which I will talk about in this December workshop actually, is fracture, straight fracture. So there are problems, contact problems. So this is subject of today's talk. And there are problems for inclusions, which maybe Sonia Mogilevskaya will talk about, I don't know. And there are also recently some axisymmetric patch load problems, which are different from contact problems actually, because they prescribe the stress on the part of the boundary. So it's not a mixed problem. It's, they have stresses everywhere prescribed, unlike in contact problems. So, okay. And motivation for studying contact problems comes from non-indentation. So in non-indentation, where experiments, which is one of the main ways to test the hardness of materials, what they do is they take a very rigid hard tip and they press it into the material and they measure the curves. So load versus penetration. And what is well known about this is that the results, the hardness of material is size dependent. So typically smaller your tip, the harder the material gets, something like that. So there is a size dependency observed over here. And of course, conventional linear elasticity doesn't explain that. Okay, so when we talk about contact problems, so plane contact problems, typically there are two types of problems people look at. So it's frictionless contact or adhesive contact. There is a contact with traction, which I'm not going to talk about today. But the conditions, and these are classical conditions without any Steigmann and Ogden elasticity, just easier to explain that way. So for frictionless contact, it's assumed that we know the vertical displacements and the tangential stress is 0 in the contact zone, so we're here. And outside, we just, over contact zone, we just assume 0 stresses. For adhesive problem, the material sticks to the indenter, and you know both horizontal displacement and vertical displacement. So those are two kind of main type of problems here. And one of the important things about these problems is they are mixed problems. So you have one type of conditions inside of your contact interval and a different type of conditions outside of that interval. And that makes it, these problems a little bit more difficult to treat mathematically, because if your conditions are the same everywhere, so for instance stresses are given everywhere, then one of the easiest things which you can do is you can take an integral transform. If it's half plane, you can take Fourier transform. If it's axisymmetric, then you can take Hankel transform. You can transform your equations into nice algebraic equations. You can solve those equations, transform it back, and you have your solution. And this works for Steigmann and Ogden elasticity as well. So it's relatively easy to obtain solutions to these patch load problems. But for contact problems, it doesn't quite work this way. And one of the problems is that the conditions are different inside and outside. Okay, so what has been done in this area? So the work in this area goes to 2011. It starts in 2011 with Gurtin-Murdoch elasticity. So majority of this work is actually about Gurtin-Murdoch elasticity. Pionichoti-Wong and his collaborators studied rigid frictionless axisymmetric problems. So they actually have contact problem over there, and they reduced this problem to a Fredholm equation of a second kind on a half axis. The kernel of that equation is not square integrable, actually, but there is this result. Then there were various results for patch load problems, strictly speaking. So for Gurtin-Murdoch elasticity and for Steigmann and Ogden elasticity. And then today we'll talk about Steigmann and Ogden elasticity for plane problems, so not for axisymmetric. As far as I know, axisymmetric problems for Steigmann and Ogden elasticity have not been solved yet, and it's not that easy. It seems not to be that easy to reduce them to Fredholm equations of any kind, actually. So anyways, so I will illustrate what what is going on the example of frictionless problem. Adhesive problem is pretty similar actually. There are some differences, but the main ideas are the same. So if we look at the boundary conditions for Gurtin-Murdoch or Steigmann-Ogden model, so you have seen that the conditions are relatively complicated, and straight contour is actually the simplest geometry where you can write those conditions. So for straight contours, everything is relatively simple. So here are our tractions, and here are our derivatives of displacements. Again, for Gurtin-Murdoch, you obtain that your tractions depend on the derivatives of displacements, and gamma 1 and gamma 2 are those surface parameters. So if a surface pre-stress or combination of Lamé parameters. And for Steigmann-Ogden model, we get almost the same thing, but we also get this fourth derivative of displacement here, so which represents essential curvature-dependence. Okay, so that allows us to write the boundary conditions, modified boundary conditions for frictionless and adhesive contact. And again, inside of the interval, we have this traction. We've added Steigmann-Ogden energy, and we are given derivative of vertical displacement. So derivative is more comfortable for me to use here. And outside of a contact interval, we have these conditions for stresses. And similarly for adhesive contact, the only thing that changes is now we know the derivative of horizontal displacement instead of tangential component of stress. So plus here means that I'm taking limits on the boundary from the side of upper half plane. I assume my material is in upper semi-plane. So I'm taking limits from the upper side. Okay, so again, I don't need to tell this audience probably that if you have biharmonic equation, you can solve it in terms of analytic functions, and you get two analytic functions out of that, and that is called, those are traditionally called Moskvishvili potentials. And those allow you to write your stresses, write your derivatives of displacements through these two analytic functions. So now we don't have to worry about biharmonic equation, we just work with those potentials. And I take it a step further. I actually will get rid of potentials as well. So for those potentials, I will take these integral representations in the form which was proposed by Savruk. So I substitute these analytic functions for these singular integrals, and G prime and Q here, those are the functions which are defined just on the boundary of a semi-plane, and they have nice geometric meanings. So it's jumps of derivatives of displacements or jumps of stresses through the boundary. Now, when I talk about jumps, again, you can think about it. I have material only in upper half plane, actually. So what's going on in lower half plane is not yet clear, and we will clarify that in a second. So what this allows us is it allows us to essentially reduce our PDE problem with boundary condition to just some kind of single integral integro-differential equation just on the boundary. Okay, so again, substituting Savruk representations into Kolesov-Moskvishvili formulas leads to relatively easy representations for tractions and for derivatives of displacements. So straight contour helps a lot with that. Typically, you would also have some regular contours, regular kernels over here in each of these equations, but for straight contour, those kernels are just 0. And so now, again, I mentioned that we have plus and minus, so we have jump. Now, physically, our material is present only in the upper half plane. There is nothing in the lower half plane. So, and what we want to do is we want to do some kind of analytic, piecewise analytic continuation of our complex potentials through this straight contour through the real axis. Again, if it's piecewise analytic continuation and there is no real material in the lower half plane, then how do we continue them analytically? It depends on us, actually, to some degree. It's on our choice. And there are several standard choices to do it. So typically, if you have stresses given on the boundary, you would continue stresses through the contour and let the derivatives jump. If you have derivatives given, then you draw it the other way around. And it turns out, and what that does is that allows you to eliminate Weidenhofer functions, g prime or q. It just automatically becomes 0 in that case. So it turns out that for me, for my particular problem, it's more convenient to do something else. And that something else is I just set my complex potentials in the lower half plane just to be equal to 0. Again, nobody really stops me from that. It's somewhat my choice how I continue them. And I just say that they should be 0. So that leads that this minus, if I look at the problem, then my displacement from the minus side is 0, or equivalently, due to existence or uniqueness of solution to this problem, I can set that the stress on the lower half plane is 0. Now, what does that give to me? It turns out that it allows me, so if I go back, if I look over here, then this thing is 0, this thing is 0, so my g prime and q are just correspondingly values of derivatives of displacements on the upper contour or values of stresses on the upper contour. So, and what I can do after that is I can take this and plug them into my conditions, boundary conditions for Steigmann and Ogden elasticity, and obtain these boundary conditions now for this particular effort. Now, since I've chosen my piecewise continuation in this form, I have to enforce it after that, but it's exactly in this form. This is where these conditions come from. So those are just result of enforcing my chosen continuation. Okay, so now essential.
Maybe I missed it, but how integrals are regularized?
How integrals are these integrals? Yeah, these integrals are singular.
Yeah, but how they understood in the principal value?
They are understood in the principal value case, yes. This is a singular integro-differential equations. Yes, exactly. So now I need to solve this particular system of equations. And my goal here is actually not to solve this system in any kind of analytic way. I kind of give up on the idea that I can write it in a nice way. My main goal here is to regularize this system. So what I want to obtain is I want to obtain how many degrees of freedom I have in this system and whether my solution exists and unique. And my goal here is just to reduce this to a system of Fredholm equations for which I can somewhat know existence of uniqueness. And typically that Fredholm system also has some kind of constants, which gives me opportunity to enforce some additional conditions on my solutions. Okay, so what do I do here? So I take a Fourier transform of these equations, and I use the relationship between Fourier transform and Hilbert transform, and I use the relationship between Fourier transforms and derivatives of Fourier transform. And once I do that, that allows me to express Fourier transforms of my functions outside of contact interval through Fourier transforms of my unknown functions inside of contact interval. Inverting that leads me to express again my unknowns outside of contact interval through inside unknowns, and substituting these back into the single integral equations, but just on the contact interval, leads me to a system of Fredholm equations of a second kind. So they might have logarithmic singularities. So the kernel might have logarithmic singularities, but aside from that, those are nice equations, Fredholm equations of a second kind, just on the interval. They look a little bit scary. Now, another thing which comes out of this is because I have derivatives in the system, I also obtain constants, free constants. So in this case, the system possesses 10 real constants, which I can fix somewhat to my liking to enforce some conditions which I want to enforce on this system. And it's pretty typical for Steigmann and Ogden problems to have 10 constants coming out of one contour. So the same thing actually happens for fracture. Now, what can be done with those constants is we can enforce the boundedness of stress and strain fields using those contacts at the crack tips. And it turns out that to do that, we need to enforce these conditions. And on top of everything, we fix the force which is acting on the stamp, and we fix the moment of the force which acts on the stamp. So formally, problems with Steigmann-Ogden surface energy possess enough of constants to actually generate the bounded stress and strain fields. So that is kind of interesting result. Gurtin-Murdoch model, which is low-order model, does not possess enough of constants to enforce that. There is just not enough of constants in the system. So you typically would have singularity still at the ends of contact interval or at the ends of crack tips, even though sometimes instead of strong square root singularity in Gurtin-Murdoch model, you will get logarithmic singularity, so weaker singularity. Okay, now another interesting thing which comes from this system is after we look at the system and we rescale it from the contact interval negative L, where L is typically the size of nanometers, to negative 1, 1, what you get is that the system is dependent on these three parameters. So gamma 1, gamma 2, gamma 3 here are correspondingly pre-stress, Lamé parameters, and bending parameter of your energy. And those parameters, they cannot be measured. Again, measuring surface tension at nanoscale in metals is complicated. So typically those parameters are obtained by atomistic simulations. But there are some papers, in particular Miller-Shenoy, where we derived Gurtin-Murdoch parameters, and Chapadia, Mahamadi, Sharma, where we derived that Steigmann-Ogden bending parameter. So there are some values for those parameters. And the typical values obtained for metals, typically, or polymers, are in this range. So gamma 1 and gamma 2 are roughly over 0.01, but gamma 3 is typically small. So it's nanometer times nanonewton, so that is 10 to the 18th, so it's small. However, those parameters are really scaled. And if you look at this scaling, you can see that if your L is small, so of order of nanometers, then those parameters actually might become prominent. So they're not tiny, not completely tiny at least. And they might affect the values of your solution. Now, another thing to notice here is this theory can be used to model, and I mentioned that, solids with coatings. And of course, that is a completely different game, right? So you can put any kind of coating you like. You can make it very rigid, and in that case, you might have these effects not on nanoscale, but on macro scales. So it's also useful for that case. Now, what is about applicability of this model? So general Gurtin-Murdoch surface energy is noticeable when your length scale is below, say, 100 nanometers. You can notice the difference between classical solution and Gurtin-Murdoch solution. Steigmann-Ogden surface energy typically becomes prominent at smaller scales. So typically you need to be maybe within 20 nanometers, and the difference will be small with Gurtin-Murdoch solution. But again, it won't be zero. Okay, so numerical results. So here are some numerical results for adhesive contact, and so these are results for different values of surface tension parameters. So starting from 0, so solid line is a classical solution, essentially. There are no surface effects. And then we vary how much these effects change, and we get different conditions. Now, one of the conclusions, which you can see almost universally, no matter what kind of problem you solve, is that if you're away from the crack tips, typically effects of this surface energy, whether it's Steigmann-Ogden or Gurtin-Murdoch, they're relatively small. So for instance, I will show you results for crack later, where it's almost the same for bulk of a crack. But usually near singularities like crack tips or ends of a contact interval, that's where the things change. So that's where the surface energy typically plays a role. And here are the results for, it's another type of results for change in contact interval, so different lengths of contact interval. And again, general conclusion here is that the smaller your structure, the higher the smoothing effect of this surface energy. the larger your structure and characteristic size, the more it attempts to go to classical solution, which is singular. So the sharper your behavior at the crack tips. So those are the results for, and these are results for adhesive contact, actually, for a slightly different problem, but it can be treated in the same way. Now, another interesting set of results, and I decided to show it here, even though I didn't talk about this particular problem, is for cracks. So cracks are also one of the problems which we like to work with linear elasticity. And again, it's possible to solve problems for cracks with Steigmann and Ogden elasticity. And there are some interesting results which come over here. In particular, it's for crack graphs, and this is why I'm showing them here. It's much easier to see the effects of surface energy. So if you look at these graphs, again, this is a graph for different values of just bending parameter. So gamma 3 is that Steigmann-Ogden, specific Steigmann-Ogden component, and it increases. And you can see that, so red is the highest bending component, and you can see that that is actually the smoothest solution. And again, if you look at these graphs, again, you can see that the solutions are almost the same on the bulk, bigger part of the crack, but then near the crack tips, there are these jumps. And again, the classical solution near the crack tips is singular. So hence, here are these jumps, but in this particular model, we can tie them back up. Now, if your surface energy parameters are very small, of course, your system tries to go to a classical state, and that leads to some difficulties, numerical difficulties with solving your system, because we have very tiny coefficients, and the solution is just not very accurate. But if it's in moderate range, then the solution is fairly good. Now, again, for the crack, this is dependence on length scale. So again, half length equal to 10 nanometers, 20 nanometers, 15 nanometers. And again, you can see that the smoothest solution is actually the one with the smallest length of crack. Again, remember that our problem depends on our problem parameters inversely depend on the length of a crack, so correspondingly the smaller the length of a crack, the larger the influence of this surface energy, the smoother your solution appears to be near the crack tips. And again, if you look at the bulk of a crack, and I don't have actually here classical solution, but classical solution will lie right here as well. So they all kind of in the bulk of a crack, they look almost the same. So it's just the crack tips which are different. Okay, so some interesting problems in this area. I guess I will be early. So there are lots of interesting problems. So bigger problem is that this model is so far exists only for linear elasticity. Again, linear elasticity is relatively simple bulk concept. So nobody said that we actually have to stop at linear elasticity. So we can select any other favorite bulk theory, and we can try to generalize, create these models correspondingly for that bulk theory. Particular two kind of neighboring ones on linear elasticities, we can either go into micropolar elasticity, which introduces additional couple with couple forces, or we can introduce a coupled phenomena such as piezoelectricity, for instance, and we can attempt to create a whole new theory based on this new bulk model. Now, comparison with experimental results is relatively difficult here, again due to the size and smallness of effects, actually. So, this would be interesting. So this theory has behavior which is generally compatible with the results which are observed in experiments, but it hasn't been verified directly against the experiments. So that would be interesting as well. Effective properties of composites is a very practical issue, right? So, and again, some work has been done in this area. Now, there are various related problems. So everything which we do for linear elasticity, which can be done using this theory. Should it be done? It's a different story, but maybe some interesting problems should be done. In particular, some of the things which I would like to note is, again, there are no axisymmetric problems for penny-shaped fractures or contact problems, so there are no solutions yet. There are no solutions actually for any shapes outside of straight or circular. So those conditions, Steigmann-Ogden conditions, they are of relatively complicated kind, and when you try to write those conditions for general contour, you end up with a big mess. So because of that, majority of solutions which you see in the literature, whether it's for Gurtin-Murdoch model or for Steigmann-Ogden model, they are typically either straight contours or circular contours. I'm not even sure that circular contour with Gurtin-Murdoch theory has been solved, so circular crack. So none of those more complicated contours have been done. Yet there are no dynamic problems, even though I would like to notice that lately there was a paper by Viktor Yeremeyev on dynamic boundary Steigmann-Ogden conditions, so maybe there will be progress in that area. And another thing which I would like to notice is numerical component. So if you look at those integro-differential equations which I have, they are third order integro-differential equations. Typically, you have derivatives of the unknowns of up to third order in those equations. And those are not typical, so there are not too many methods I'm aware of which actually solve those equations. And so there is a need for reliable methods, and we worked on this area, and it appears that B-splines, approximation by B-splines, might work fairly well for these types of equations. There is still some extension which needs to be done with those methods with B-splines, but those seem to be working well and resulting in linear systems with nice condition numbers as a result. Okay, so that's the end of my talk. Thank you very much.
Let me ask a simple question about size-dependence. When this essential image problem from classical to size-transition, when it is important? Just on time.
So the classical case works well for macro objects, right? And for macro objects, those parameters, scaled parameters which I have shown, they are tiny. So even if you put this Steigmann-Ogden elasticity for macro objects, you won't see the effect of it because those parameters will be divided by L cubed, they will be tiny. So your equations will be essentially the same as classical equations, and your results will be essentially the same as classical equations. Now when you go to small scale, again you divide by L, so your L becomes smaller, so those parameters are not tiny anymore. And the exact range where this becomes important is somewhere between 100 to 1000 nanometers, exactly the nanoscale, hence title of my talk, and especially between 5 to 100 maybe, which is so not too small, but not too large, so you see the effect. So. Mm-hmm.
Quick question and a comment. So I'll make a comment first. So regarding on your conclusion, you said something about solving singular integral equations with high accuracy. And I don't know the elasticity field as well, but I know there's a huge literature in wave scattering
Mm-hmm.
and fluid dynamics. So you might look at those for solving
Okay.
integral-differential equations.
Integro-differential. Okay. I checked, and my check didn't result into anything, so I decided to invent my own.
Yeah, that's fine. But it's probably because of the elasticity.
Mm-hmm.
There's less of that.
Okay.
But the second thing is, I once worked on a problem where the model was very similar to yours. It didn't have as much, it wasn't as complicated for the surface stress.
Mm-hmm.
But we were mostly interested in the phenomenon of surface diffusion. So it was also a nanoscale problem.
Mm-hmm.
Where
Mm-hmm.
you would get motion of the boundary via surface diffusion. I was just wondering if that's important in your area as well.
Well, there's no motion here.
So you typically don't have surface diffusion.
I don't have, yes, it's a static problem. So the only thing, all the problems which I talked about today, which I shown best.
But in the experiment phase, is it important surface diffusion?
It might be. I don't know. might be, because experiment when we indent, we do it with some time. Yeah.
So on a related note, those models are based on the small strain approximation, right?
Yes.
Is there a chance or hope to go beyond that?
I don't know. So you can try to put non-linear elastic energy in that model. In that case, of course, you have to be very careful differentiating between your deformed state and undeformed state. So that's one of my interests. To be honest.
Is it tractable?
Is it what?
Tractable.
Tractable. Hopefully. You will need to put a different model on the surface. Yes. 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 Should be in the same way as it's, well, non-linear elasticity is kind of complicated, but in a similar way, probably.
On those photographs at the start, you had some little bars showing the scale. I thought they indicated microns.
They indicate
very much larger than nanoscale.
Micron. Yes, we did. Again, that's just a picture I found on the internet.
Yeah, but I think you will find it is a little UN, which is
yes, I know it's 1,000 times, but yes, but again, I said between 1 and 1,000, so it's kind of borderlines in that onto that. And if you look at those, we have a lot of tiny details when micron, right? So so the scale which shown here is micron really, but yeah, but there are lots of things inside. So yes.
Is this your system of equations?
Yes.
So, well, of course you can formulate a matrix with the problem, but there is no way to do something with the factorization of the matrix.
No, probably no. That's why I work exclusively. I like Riemann-Hilbert problems, as you might know, but that's why I work with single integro-differential equations, because I can say at least something about solution of this, and then I can solve them numerically after that. But with Riemann-Hilbert problem, essentially the derivatives, with Riemann-Hilbert problem, derivatives will spoil it all, kind of. It's just two functions, yes. But the problem is that G prime is my unknown, but then I have Fourier derivative of G prime sitting in there. So it's kind of, that's what makes it difficult to deal with Riemann-Hilbert. Because traditionally, all this area is Riemann-Hilbert area, essentially, for classical problems. Thank you.